Hello students, welcome to the course Electrical Circuit and Network. Myself Bilan Sasmal from Department of Electrical Engineering from JIS College of Engineering. Okay. So as already we have seen what is the Laplace transformation, why it's required, and what are the different Laplace transformation for different function, different time domain function, that already we have seen, and similarly we have mixed the table for that and for our regular use or for our next calculation procedure, right? So today we will see that how we can apply this knowledge or this concept of Laplace transformation to the electrical system. So electrical system means already we know the system where some resistance, some inductance, some capacitance will be there, as well as with some sources. The sources may be of DC types or maybe of AC types, whatever is this. For any practical sources or any practical circuits will be there, and where we have to identify or we have to solve that circuit by using the concept of this Laplace equation. So the first thing, whenever we are going to solve these types of electrical circuit by using this Laplace transformation, so what are the steps or how we can do that? So there are two different options. So the first of all we consider the option one, that is write the set of differential equation in the time domain and describe the relationship between voltage and current for the circuit. So first of all we are writing the equation in the time domain. So there may be if there is suppose there is some inductor, then if we want to find out some voltage across the inductor, then obviously the L di dt terms will be there. Similarly the current to the capacitor, there in any places for inductor and capacitor there may be some derivative portion, there may be some integration portion. So based on that thing we have to write down the equation in time domain, and then we have to apply KCL and KVL. This is the basics of for electrical circuit, and already we have discussed what is KCL and KVL. So use the knowledge of that KCL and KVL and the laws governing the voltage and current for the resistor, inductor and capacitor, and then Laplace transformation of the equation to eliminate the integral and derivatives and solve these quantities for V of s and I of s. It means ultimately whether the circuit or the equation which is determined or which is derived from the equation contains some derivative part or some or some integration part, and to solve this circuit, which is very difficult, so we will apply the Laplace idea of this Laplace transformation, and we will solve it, and whether our ultimate portion, that is voltage or the current, that will be in terms of S domain, and then again we have to convert that S domain parameter into the time domain parameter. It means again we have to do the inverse Laplace operation to get the actual actual value of voltage and current as there in time varying quantity. Okay, so let's see how we can solve these types of problem. So these are the one method, and similarly there is one another method also, or that we can see in option 2. Okay, so in option 2 there is the Laplace transformation of the circuit and use DC circuit analysis to find V of s and I of s, and then again taking its Laplace transformation to get V of t and I of t. So in the second case, where the DC circuit or AC circuit, whatever the circuits are there, so first of all at the starting, at the first we will apply the Laplace transformation for the whole circuit, then whatever the equation comes, then we will take it in the inverse Laplace operation. So what are the basic difference between these option 1 and option 2? The basic difference is that for the previous option, it means if we go for the backward, so the backward option here, first of all we are writing all these differential equation over there, and then we are writing the KCL and KVL equation in terms of time domain. Then we are converting this time domain equation, or we are solving this equation in terms of S domain or we are taking Laplace over there after finding the KVL or KCL equation. Then again we are doing the inverse Laplace operation. This is the option 1. And similarly for the option 2, that was at the first time, at the very first, we are applying the concept of this Laplace, or similarly we are transferring all the quantities are available within the circuit, that is in S domain, and then again we are applying the KCL or KVL, whatever we have, whatever is there, and then we are applying inverse Laplace to get the actual equation, right? Okay. So now if we consider that a circuit having may have some resistance, circuit may have some inductance, circuit may have some capacitance, so it's better to check whether what will be the Laplace transformation for each and every separate element. It means if we consider the resistance right now over here in time domain, we can write simply that the voltage across the resistance, that is if we consider V of t, and if the current flowing through the resistance, that is I, and in time domain we can represent it at I of t. So simply we can write, as per the Ohm's law, we can write V. Normally we know that V is equals to IR. Similarly, if in time domain we can write that V of t is equals to R I of t, it means both V of t and I of t they are in time domain, right? Similarly, in case of Laplace transformation, or in case of S domain, it means whenever we are considering this Laplace transformation, then our V of t, that is the function in time domain, so this function has been converted as a V of S. And similarly this R is a constant, this is not dependent on time, so there is no more changes, and this I of t, this function, that is time domain, it's dependent on the time, so that's why this I of t, this function is in time domain, and whenever we are going to change it as in S domain, or by taking Laplace, if we are taking Laplace, then it will be changed into I of S. So simply for time domain to S domain conversion, if we consider V of t is equals to R into I of t, that is our time domain equation. Similarly for S domain equation, we can write V of S is equals to R into I of S, or separately also we can write that I of S is equals to V of S divided by R, no problem at all. It's just like the previous cases, or just like the normal cases, whatever we have written in previously, everything will be over here, no problem at all. Okay, so similarly as there is a resistance, then there is no more problem, but if in place of this resistance, if there are any inductance or capacitance, then what happened? Okay, so if there are any inductance, then, so normally for any inductor we know that there is an inductor, and obviously we are considering in time domain, for this time domain cases, and I amount of current which is flowing through the inductor, and amount of current which is flowing through the inductor, and V, that is the voltage across this inductor, and L, that is the values of this inductor, and where this is the I0, that is the main concerned thing. I0, that is the current at initial condition. So at initially there is a I0 amount of current. So whenever we are considering in normal time domain analysis, in our circuit analysis, then we cannot apply these things, these previously charged or previous some contents thing, or initial condition. So for this initial condition, if we want to consider this thing, then obviously we need to go for S domain analysis. So similarly, if we go for S domain analysis, then obviously we know V of t, that is the S domain analysis, that is V of S. And similarly, and next is L di dt, and L into di dt. Di dt is nothing but it's a derivative of I of t, and normally we know the I of t, that is the time domain function, and the Laplace, if we consider the Laplace of I of t, it will be obviously I of S. But here look the thing carefully, here whenever we are going for the Laplace transformation, it means we are going for the Laplace transformation of overall portion. Similarly for this case, we are going for the Laplace transformation for overall this function, it means Laplace of overall this function. So here L, this L is nothing but an inductor, this inductor value, and then it's multiplied with the derivative of this function I of t, its first derivative. Then what do we know? as per the previous formula. That is L is our constant, so where we can write that Laplace Laplace of d I of t and dt, if we write in such a way, and if we consider the Laplace transformation, so it means Laplace is over here. So similarly we can write for this, it will be s multiplied with I of s multiplied with I of s minus initial condition. So what is the initial current? That was I0 amount of current. So we have to subtract that initial amount of portion, or the initial value of this function, initial value. So as for V of s, we can write over here, so L is multiplied over here, we can take a common of L, so for within that whole portion, so s will be multiplied. So if this L is multiplied over here, so it will be L into s into I of s, so that is L into s I of s minus L into I0 minus L into I0, this term. Similarly, if we consider that I of s, what will be the function of I of s if we consider? So we can consider that I of s is equals to V of s minus of L into I0, that we can write. So again we can write that V of s minus of L into I0 is equals to our s into L into I of s. So again, if we consider that I of s, so this term will be over here, so V of s, so this s into L, this term will be in this side. So here V of s is divided by s into L, and here this term will be divided by s into L. So this L and this L will be cancelled out, so it will be I0 by s. So it will be I0 by s, and obviously for this thing, if this Li0 that was in minus, so in this side here it will be plus, obviously V of s0 plus Li0. Okay, so ultimately we are getting I of s is equals to V of s divided by L into s plus I0 divided by s into L. That thing we are getting. Okay, now the thing is, how will be the circuit? So as from the first equation we can see that V of s voltage, that is equals to SL into Is minus of Li0. So if we consider an inductor is over there and inductor value and inductor, it changes to S into L, because for S domain analysis inductor L is changes to S into L, because we know that the for time domain analysis also we have written that in place of L, that is equals to omega L, j omega L, we have written j into omega into L. So in time domain, in S domain analysis, obviously this j omega is nothing but written as s. Simply, if we want to remember this thing, this j omega is written as s. So what we can write, that is s into L. So this inductor is obviously SL, and if I is the amount of current, and obviously in Laplace domain, obviously the current should be I of s. So here the current should be I of s. We have to consider if I of s amount of current is over here. So what will be the voltage across this inductor? The voltage V of s, this is the voltage across this inductor. So V of s, this whole part. So V of s, this overall voltage is equals to Ls into I of s in Laplace domain if we consider. So Ls is the impedance that we consider in S domain for the inductor, and similarly, and I of s is the current. So the voltage for here, that is voltage only for this portion, only for this inductor, the voltage is over here, that is nothing but a S into L into I of SL into I of S, SL into I of S. This is my voltage. Okay. Now, as per Laplace transformation, our Vs overall voltage, that is SL into I of S minus of Li 0. So this amount of voltage should be minus or should be subtracted from this voltage. So if this voltage is subtracted from over here, so obviously we have to add one more voltage, one more negative of this amount voltage. So negative voltage means we are adding one sources over there having a values of L into I0, and as the minus sign is over here, that's why we are adding one sources over here in negative direction. So this voltage, what is this voltage? If we consider from upside to downside, this voltage is up to down, up to down. If we consider this side is positive and if we consider this side is negative, so up to downside the voltage is minus of L I 0, Li 0. So this voltage is subtracted. So what is the circuit? For the inductor, there is only inductor for the time domain. Similarly, for the S domain, we can see the same inductor now is being converted to a inductor having the impedance L into S in series with a voltage source, having a values of L into I0. So this is very important thing, okay, that we have to look after. Okay. Similarly, for the same thing, if we want to change it in a here one impedance which is in series with some voltage sources. So as per Thevenin's theorem, we can say yes, one source is connected with one impedance in series, and we can connect any of the other sources or any of the impedance as a load, no problem at all. Similarly, if we want to convert this source or this circuit as per Norton's theorem or as per Norton circuit, if we want to find out the Norton equivalent circuit for this one, it means this is a voltage source. So this voltage source should be converted in current source, and obviously we know in case of Thevenin's theorem, what impedance is connected in series with the voltage source, the same impedance will be connected in parallel with the current source, but the values of the current source will be the different one. So what is the values of current source if we want to calculate this one? So let's erase this one. So if we want to consider this one, so as per normal rules, we know that our I is equals to obviously V divided by Z. So as per our voltage, as per Thevenin's theorem, this is voltage is Li 0. If voltage is our Li 0 and our impedance is S into L, so L cancel out, so I0 by S, that is the amount of current source. If we want to convert this, and as this impedance is connected in series with this voltage source, so similarly the same impedance will be connected in parallel with this amount of current source. So this is the new amount of current source, and we have to connect this resistance in parallel with this one, right? So it means they will be in same circuit. So if we transfer it, so this amount of source, and what will be the source direction? As the positive direction is downwards, so obviously the source, the current source having the direction in downwards, obviously. So this I0 by S amount of current, I0 by I0 divided by S amount of current, that is downwards, and similarly this amount, the same amount of resistance, that is L into S, that particular amount of resistance which is connected in parallel with that current source, that is over here, right? And the same current I is flowing over here. So this circuit and this circuit both are same. Now choice is yours. You can apply this circuit or this circuit. It means whenever there are any inductor present in your circuit, and whenever you are going for the Laplace transformation, and if the previous current or if the initial current that is present over there, if the initially some charges are stored over there, then to consider this initial condition, you have to consider the inductor either in series with this voltage source or in parallel with this current source. Or if you consider in series with this voltage source, then obviously the amount of this voltage source will be L into I0, and inductor should be considered as a S into L. And if you consider as a parallelly, it will be I0 divided by S amount of current source, and in parallel with S into L amount of inductance. Okay. So be careful. So we can write for our further use. So if there are any inductor, if so first let it erase it first. So we can write if there are any inductor. So for inductor, this is inductor, not Laplace sign, inductor, we can simply write, just we will write one source, the source value, source, the source value, that is L I0. If we want to use the voltage source Li0, then series with Li0, voltage source Li0, and series CRIES, and in series with Ls, right? This is one portion. Or another portion we have to write that current source, this is the voltage source value, obviously voltage source Li0, or if we consider the current source is if there is a current source, then obviously the values of current source will be I0 divided by S, and parallel with Ls. So take a note. So this one is very, very important. Okay. Okay. Similarly, for capacitor, what will be the equation? Just like the previous one, for the capacitor also we can write it. Okay. So how we can do that? For the capacitor, we know if I is the amount of current through the capacitor having the values of C, and the capacitor, there is initially the capacitor, there is a voltage of V0, if we consider this one. So then we know that the I of t, it means current in the capacitor at any time. Now we can write that C is equals to C multiplied with dV dt, C multiplied with dV dt, and V of 0, that is equals to V0. It means initially the capacitor having a voltage of V0. Similarly, for time domain to S domain analysis, so we have to take a Laplace. Again, I of t having a Laplace, that is I of S. I of t to I of S. Similarly, C, that is the capacitor, that is independent of type, so there is no more changes. C will be normally over there, and V of t, only for V of t it will be V of S. Only for V of t it will be V of S, but there is the derivative portion. As there is the derivative portion, so just a few seconds ago we have seen for the inductor that if there are derivative portion, so what we can write? We can write that C multiplied with S into V of S, S into V of S. So we can write over there. So if we take the Laplace in both the side, so it means we are taking Laplace from this side, from time domain to Laplace domain or S domain analysis. So we have to take the Laplace for both sides. So if we take the Laplace, then it comes like this. So C is our constant, and then we have that will be our V of S, S into V of S, S into V of S minus V0. V0, that is the initial value. Okay. So if we multiply it, that will be C into S V of S minus C into V0. So that is written over here. So similarly, for this circuit also, if we want to draw the circuit, if we want to use, if we want to design the circuit, then what happen? What will be this thing? So here current is over there, I of S, also this current. So this current is I of S. I of S is equals to, based on this, that this voltage is V of S voltage. So this if we consider first parallel circuit, then there is one option, and if we want to consider the series circuit, then there is one option. So better to consider first the series circuit for the better understanding, just like the previous one. So if we consider that the I of S is the amount of current, so first of all there is a capacitor, and as there is a capacitor, we know what to write. So for capacitor we write j 1 by j omega c, 1 divided by j omega c, that we write. So now j omega is equals to s, so in place of c, j omega is equals to, we know, s. So we write in place of c 1 divided by sc, 1 divided by sc. So for the capacitor it will be 1 divided by s into c. So as this is my capacitor, so this is the amount of current. Okay. So in capacitor we can write 1 divided by sc, and similarly from this equation, if we want to consider the series circuit means there will be the summation of voltage, there we can, or for parallel circuit there will be there we can get the summation of current, because for parallel circuit the voltage will be same always, and for series circuit the current will be same, the voltage will be the different one. So we have to change the equation in such a way. So if we find v of s, so it means we are just taking in left hand side in s of c, sc v of s is equals to, that we can write I of s, we can write I of s plus c of v0, and similarly if we take it this side, so sc will be cancelled out and sc will be over here divided by sc, and also divided by sc, no problem at all. So v of s, that is the overall voltage across the capacitor. So what we can write, so if we write a capacitor over here, so one capacitor c, and the value is 1 divided by sc. Okay, so if through that capacitor, if the current amount is I, or for Laplace domain if we consider the current I, means here the I of s current is there. So what will be the voltage across this capacitor only? Across this capacitor the voltage, that will be, we know V is equals to I into Z. So we know V is equals to I multiplied with Z. So what is the values of I? That is I of s. So I of s and multiplied with Z means 1 divided by sc. So I of s by sc, I of s divided by sc. So we are getting this amount of voltage, so this amount of voltage is present across the capacitor. Okay, so across the capacitor, so and remaining the overall voltage, that is V. So this overall voltage V now is this voltage, it means voltage across the capacitor plus this voltage, it means CV0 divided by SC, it means C is cancelled out, so V0 by S, this amount of voltage should be added, there is a C and C cancel, C and C, numerator and denominator, C and C cancel out, so there is V0 by S. So this amount of voltage is added over here, so we have to add this amount of voltage, so upside will be plus, downside will be minus, and this voltage source having a values of V0 divided by S. So now whatever the circuit of this point and this point, these 2 points having the values of, that is this value, that is V of S. So this value is actually V of S over here, V of S, right? So now this is our circuit. If we erase this portion, so it will be very clear, okay. So this voltage is over here. Now just like the previous one, this is our Thevenin equivalent circuit. Now if we go for the Norton equivalent, so source will be just we have to consider the source conversion method. So for the source conversion, simply we can say as there is a voltage source in series with the capacitor, so for the source conversion with the current source, so current source value will be I is equals to V by Z. So if I is equals to V by Z, so V value is V0 by S, so V0 divided by S, V0 by S again divided by 1 divided by SC. Okay, so it will be V0 SC divided by S, so ultimate value will be V0 into SC divided by S. So this S cancel out, so only V0C, that will be current source value. So the current source value is C into V0, that is over here, and the same amount of capacitance that will be, that previously was in series with this voltage source, the same value will be in parallel with the current source. So now 1 by SC, that will be parallel with the current source. So the remaining circuit is same. Okay, so now for the capacitor, we can say if there is any capacitor in normal circuit, for time domain analysis there was the only capacitor. If we want to convert this circuit in Laplace domain first or in S domain first, obviously we have to consider either a voltage source in series with 1 by SC amount of capacitor and the voltage amount is V0 by S, or we have to consider C V0 amount of current source in parallel with 1 by SC amount of impedance for the capacitor. So either we have to consider this amount of current source or we have to consider this amount of voltage source if the capacitor having some previous voltage or some initial voltage, right? So this is the basics of this resistance, inductance and capacitor for the time domain to S domain analysis. Okay, that's for the